we're asked to find or explain clearly why the boiling point of ethanoic acid is higher than that of propan-1-ol. So again, you're looking at ethanoic acid. If you want to look at ethanoic acid has got this functional group, C double bond O and OH. And propan-1-ol would be along the lines of this, where you just have the OH group. So over here, what you actually have is much stronger bonds because of the carbonyl group and the OH group. And we saw this in the last video. Ethanoic acid has much more stronger hydrogen bonding than propan-1-ol would have. So between the molecules, you have hydrogen bonding. There is also hydrogen bonding, not just in ethanoic acid, but there's hydrogen bonding between the alcohols as well. But the hydrogen bonding is stronger in a C double bond O OH group. And again, if something is stronger, you're going to need a lot more energy in order to break those bonds, which gives rise to the higher boiling point. The next one then, part D. What is the organic product of the reaction with C with dilute acidified potassium permanganate? Let's see. Give me 1 second, I'll just make a bit more space. So compound C is propanal. So this is an aldehyde. And KMNO4 is an oxidizing agent. Quite a strong oxidizing agent. So if you have gone over the previous video, you should know that an aldehyde, when it's oxidized, will produce carboxylic acid. So obviously, if it's propanal that's being reacted with, you're going to form the carboxylic acid version of it, which is going to be propanoic acid. Now, all of this is got from the basic fact that an aldehyde, when it's oxidized, will produce a carboxylic acid. And again, this is when it's in excess. You can also have another oxidizing agent if you wanted. If you had something like sodium dichromate, Ne2Cr2O7, that would also work. So propanoic acid. So let's have a look at the last part. Write a balanced equation for the reaction that occurs between sodium and B. So again, I'm guessing B is an alcohol. That's one of the things you have to learn, is the reaction of an alcohol with sodium. And B is, let's see, B is propan-1-ol. It is an alcohol. Okay, so let's have a look at it. So we have propan-1-ol, and we're reacting with sodium. So in the previous notes that I gave you, you'll find that it was actually, I think, ethanol that we reacted with sodium. You have to be able to work between the different alcohols. The result is generally still the same, but you have to be able to work through them. So first of all, we're going to write out what propanol is. So when you're looking at propan-1-ol and you're looking at the structure, and you count up the carbons and the oxygens and the hydrogens, what you end up with is C3, and we have H7 and an OH then at the end. You're reacting with sodium, and this sodium takes the place of the hydrogen. So you end up producing C3, H7, O, Na, and plus hydrogen gas. Now you're going to have to go back and then balance this equation. So when you count up all the carbons and you start balancing, we look at 3 carbons on the left and 3 carbons on the right. That's fine. And then you have to start counting up the hydrogens. So obviously there is only 1 hydrogen here on the left, so we're going to have to double this. So we end up with 2CH3ONA plus, so we've doubled the carbons there, so we've got to double the carbons on the right hand side. And then that should be it. That's it balanced. Let's move on to the next one. The next one is 2017. So we're not doing this particular part here. We're looking at the structure of eugenol. So the structure is shown. Write the molecular formula of eugenol. And this is just a case of counting up all the carbons. just bearing in mind in this benzene structure, you have 1, 2, 3, 4, 5, 6 carbons in there. And then also don't forget, which I think came up in your mocks as well, off this benzene structure you also have hydrogens coming off here. Obviously with the OH group here you're not going to have a hydrogen there, but you'll have a hydrogen here too. And so make sure you take that into account when you're counting it up. If you haven't done it already, go and count it up and pause the video. So if you have counted it up, so the molecular formula of eugenol, you can do it in a couple of ways, but generally you start with C10, it's going to be H12 and then O2 from my count. So you can also, it will allow another version where it'll actually, if you write down, 10 carbons, 2 oxygens and 12 hydrogens, it will allow this, but to be honest, this is the best answer and don't take a chance. Name a spectroscopic technique that could help confirm the identity of a sample of eugenol. So IR spectroscopy is generally what we'd use. If you said any other type of spectroscopy, that would also do. So for example, you could say a mass spec, which we have looked at before. Next, question 8, and we're on to 2017. Scheme below shows redox reactions of some organic compounds. Have a quick read through that question and we'll be back in 1 second. So the first part of question 8 is about the experiment, and I'll be going through that full experiment in a later video. The one I'm interested in is really the reactions for the moment. So at the moment I'm interested in this bottom part here. So copy the structures of phenylmethanol and benzoic acid into your answer book and mark clearly the bonds involving carbon in this oxidation reaction. So of course phenylmethanol is oxidized to produce benzoic acid, and we've drawn them out. So this particular substance here is phenylmethanol. And you can see that. So often this benzene compound, when it's in a structure, is often called a phenyl group. And you can see we've got a methanol then here beside it, a single carbon, which is meth, and then the OH, which gives you the ol. Over here on the right hand side we have again this benzene ring, and you have a carboxylic acid functional group here. So this is going to be your benzoic acid. So where are the bonds broken? Well, for phenylmethanol to be converted into benzoic acid, this bond here has to be broken here, and this bond here has to be broken here. And once those bonds are broken, then that forms your benzoic acid. It also wants you to identify which bonds are formed in benzoic acid, and that should be clear enough that this is a new structure. Obviously the OH remains constant in both molecules. Part B, give the IUPAC names for A and B and draw their structures. So we're going back up here to have a look at A and B. So normally what I would do here is, before I answer the questions, I would look at the diagram, and before I answer any questions, I would just try and figure out from the diagram what A and B is. That would be my first step in an exam. So let's have a quick look at it and see what we can come up with. We have an alcohol, which is here. So that is propan-1-ol. We have Na2Cr2O7, and if you watched the previous video, you should know already that that is an oxidizing agent. So an alcohol, when it's oxidized, will produce A. And then A is going to produce propanoic acid. So what we've got is an alcohol going to something and continuing on to a carboxylic acid. And there's only one thing that this can be, and this one in here is going to be an aldehyde. It has to be when it's oxidized. So what aldehyde is it? Well, if you're starting with prop and you're ending up with prop, you're going to have to go through prop in the middle. So that means A is going to be prop, and it's going to be an aldehyde, is propanal. I would then look at the next one then, where propan-2-ol. So what's the difference between propan-1-ol and propan-2-ol? Both of them are alcohols. Again, if you looked at the previous video, you'll know that propan-1-ol is a primary alcohol. Propan-2-ol is a secondary alcohol. Now when you oxidize a primary alcohol, you get your aldehyde up here, but when you oxidize a secondary alcohol, you will get a ketone. So this one in here is a ketone. And again, if you've propan-2-ol and you oxidize it, the appropriate ketone then is propanone. which is also propan-2-one, as we saw earlier on. If you want to go from propanone, and you can see here there's two arrows in here. There's one going backwards as well. So how do we get from propanone back to propanol? And again, from the previous video, you should know that that is based on hydrogen with a nickel catalyst. So before we've answered any questions, we've filled in all the gaps that we've come up with, and this should make our questions a little bit easier. So let's skim down through it. Give the IUPAC names for A and B and draw their structures. So A is going to be propanal and B is propanone. So A is propanal, B is propanone. And actually a lot of students make the mistake here of only putting in the names, and they actually just forget to draw their structures. Always bear in mind this is 12 marks. So there's a lot of marks going for this. So that should indicate that you need more than just 2 names. So propanal, 3 carbons, double bond and a H, and your single bonds. Your propanone then is the same thing, C single bond C, and the double bond, of course, of propanone always goes in the middle. You can't put it at the end, of course, because if you put it at the end, then it just becomes propanal, which is what you have at the start. So that's why propanone has to go, the double bond O has to go in the middle. So part C then, identify the reactant and the transition metal catalyst used to reduce B to propan-2-ol. So again, the reactant is going to be H2 and nickel is your catalyst. So fairly straightforward once you know the answers, I suppose, as everything always is. Let's move on to part D. The oxidation of B is very difficult, while A can be very easily oxidized with reagents that are weaker than those in the scheme. Suggest a weak oxidizing reagent, a transition metal compound, that could be used to distinguish between a sample of A and sample of B. Okay, let's clear a bit of space here. So basically in this question here, you're being asked, how do you distinguish between a sample of A and a sample of B? In other words, how do you distinguish between an aldehyde and a ketone? So this is one of the last couple of tests that we didn't get a chance to do before we broke up for school. I sent you videos on them. The videos are really clear. You should look at those videos and make sure you understand them. Any questions, just come back to me. But if you want to distinguish between an aldehyde and a ketone, there's several different ones you can do. So one of the things you can use is you can use Tollin's reagent. And that will do, that will get you your 6 marks. There is another one that's often used, which is Failings, and you may have used that in biology if you do biology, Failings A and B. That will also get you 6 marks as well. That's part D. Part E then, name an ester that is a structural isomer of propanoic acid and identify the alcohol and carboxylic acid. Okay, so I'll just draw out a molecule here, be back in a second. So what I've done here is I have drawn out propanoic acid. And what I would do here is I would redraw the molecule. If you want to find an ester, we know that an ester is COOR. So what I would do is I would take out that hydrogen there and I would bring that hydrogen over here and pop it on the end of that bond here, and I would take this CH3 group and bring it back and put it in here. And that sounds a little bit long-winded, but if you redraw it, look at what you end up with. You end up with C, single bond C, double bond O. Your hydrogen goes on the left-hand side. And down here, you have a CH3 group. You've just switched the hydrogen with the CH3 group. And now you've got an ester. So this ester is going to be ethanoate, because you've got 2 carbons here and here. And the type of ester it is methyl ethanoate. So that's the end of that one. I'm sorry, I forgot that you also have to identify the second part of this, identify the alcohol and the carboxylic acid. And again, you can go back and check the notes, but the methyl is coming from the methanol and the ethanoate is coming from ethanoic acid, because an alcohol plus a carboxylic acid will produce an ester and water.